something impossible happened at perihelion. Between October 29 and October 30, as 3I Atlas swung behind the Sun where we could not see it, spacecraft watched it turn bluer than the Sun itself. Not slightly blue, bluer than a 5,800-degree star. And then it accelerated. 135 kilometers per day squared of thrust with no visible source. NASA went silent during a government shutdown, and the images from Mars, the ones that could have answered everything, disappeared into bureaucratic darkness. Avi Loeb calculated that if this is natural, we should see a massive gas cloud in December, 10% of the comet's mass ejected into space. If that cloud is not there, if his prediction fails, then we are looking at something that does not fit any model we have. 9 documented anomalies, 9 unexplained properties in one object, and the mainstream scientific community is fighting about whether we should even be asking if this might not be a comet at all. December 19th. That is when 3I Atlas makes its closest approach to Earth. That is when every major telescope will point at this visitor from another star system and finally tell us what we are really looking at. But right now, today, the data we have is already breaking the rules. If you want to stay updated on what might be the most important astronomical observation of the decade, make sure to like this video and subscribe to the channel. Tell me in the comments where you're listening from, what time it is there right now, and whether you think 3I Atlas is just an unusual comet or something more. If you want to help our community grow and make sure more people know about what is happening with 3I Atlas, share this video on social media and press that notification button so you do not miss the updates as December approaches. Your support means everything, thank you. The impossible blue shift. Let me explain why that colour matters so much, why this is not just another interesting observation to file away in the catalogue of cosmic curiosities. When we see colour in space, we are seeing chemistry, we are seeing physics, we are seeing the fundamental processes that govern how matter interacts with energy. A red comet tells us about dust particles scattering sunlight, about carbon compounds absorbing certain wavelengths while reflecting others. A green comet speaks to diatomic carbon molecules being excited by ultraviolet radiation, fluorescing in that characteristic emerald shade we have seen in dozens of solar system comets. But blue means something else entirely. Blue means emission, not just reflection. Blue means something inside or around 3I Atlas is generating light in wavelengths that should not dominate the spectrum of a frozen ice ball heated by a distant star. Avi Loeb put it bluntly in his analysis. Dust is expected to redden scattered sunlight. The surface of 3I Atlas should be approximately 20 times colder than the Sun's photosphere, resulting in a redder colour, not a bluer one. For this object to appear bluer than the Sun defies the basic thermodynamics of how cold bodies interact with stellar radiation. The colour journey itself tells a story that does not quite add up. Just months ago, in July and August, 3I Atlas was red. Deep images from ground-based telescopes showed a reddish hue, exactly what you would expect from a dusty carbon-rich body heated by solar radiation. Then in September, during that total lunar eclipse when amateur astrophotographers Michael Yeager and Gerald Riemann captured their stunning images from Namibia, the comet had shifted. Green, blue, green. A classic diatomic carbon emission that made it look like any other comet approaching the inner solar system. Now it is blue. Intensely, impossibly blue. And the implications of that colour change are keeping some of the brightest minds in astronomy awake at night. Let me explain why this matters. Why this is not just another interesting observation to file away in the catalogue of cosmic curiosities. When we see colour in space, we are seeing chemistry, we are seeing physics, we are seeing the fundamental processes that govern how matter interacts with energy. A red comet tells us about dust particles scattering sunlight, about carbon compounds absorbing certain wavelengths while reflecting others. A green comet speaks to diatomic carbon molecules being excited by ultraviolet radiation, fluorescing in that characteristic emerald shade we have seen in dozens of solar system comets. But blue means something else entirely. Blue means emission, not just reflection. Blue means something inside or around 3I Atlas is generating light in wavelengths that should not dominate the spectrum of a frozen ice ball heated by a distant star. Loeb put it bluntly in his analysis. Dust is expected to redden scattered sunlight. The surface of 3I Atlas should be approximately 20 times colder than the Sun's photosphere, resulting in a redder colour, not a bluer one. For this object to appear bluer than the Sun defies the basic thermodynamics of how cold bodies interact with stellar radiation. The data comes from multiple independent sources, which makes it impossible to dismiss as an instrumental artifact or an observational error. Stereo A's twin cameras, the HI-1 and Core-2 instruments, both recorded the blue shift. Soho's LASCO C3 coronagraph confirmed it. GOES 19, a weather satellite that happened to be monitoring solar activity during the critical window when 3I Atlas was behind the Sun from Earth's perspective, captured that same impossible azure glow. These are instruments designed by different teams, operated by different agencies, processing data through different pipelines. They all saw the same thing. And what they saw was light being emitted, not merely reflected. This is the crucial distinction that separates a curiosity from a genuine mystery. When sunlight hits dust or ice, it bounces off, scatters, reflects. The colour we see is the colour that survives that interaction, the wavelengths that did not get absorbed by the material. But emission is different. Emission means something is glowing. Something is releasing energy in the form of photons. Something inside or around 3I Atlas is hot enough, or energetic enough, or strange enough to pump out blue light that overwhelms the reflected sunlight we should be seeing. The obvious explanation, the one that every scientist reaches for first, is gas. Ionized gas, specifically. When molecules in a cometary coma get hit by solar ultraviolet radiation, electrons jump to higher energy states. When they fall back down, they release photons. Different molecules release different colours. Carbon compounds can glow blue under the right conditions. Maybe, just maybe, 3I Atlas has such an unusual composition, such a high concentration of volatile carbon species, that it is generating this blue emission through straightforward photochemistry. But here is the problem with that explanation. The spectroscopic data we have from earlier observations does not support it. Remember those Keck telescope observations from August 24? Remember the Very Large Telescope data from August 25? They showed something peculiar. 3I Atlas has an unusually low abundance of carbon chain molecules, the C2 that usually makes comets glow green, the C3 that contributes to the overall colour signature. The ratio of cyanogen to carbon chains is one of the highest ever measured in any comet. The paper by Luis Salazar Manzano from the University of Michigan stated it clearly. 3I Atlas is among the most carbon chain depleted comets known, so if it does not have the molecules that typically produce coloured emission, what is making it glow blue? This is where the speculation begins, where the boundary between orthodox science and uncomfortable questions starts to blur. Some researchers have suggested that the blue emission could come from carbon monoxide molecules being ionized at extremely high rates, producing a blue fluorescence that we have simply never observed at this intensity before. Others point to the bizarre nickel signature, that puzzling emission of nickel without iron that has been one of 3I Atlas's most persistent anomalies. Could nickel compounds, energized by solar radiation, be contributing to the blue glow? We know that nickel tetracarbonyl breaks down under ultraviolet light, releasing both nickel atoms and carbon monoxide. Could some exotic chemistry involving those breakdown products be responsible? But Loeb, predictably, goes further. In his analysis of the perihelion observations, he raised a possibility that most of his colleagues would prefer to ignore. What if the blue colour is not about chemistry at all? What if it is about heat? Not the passive heat of solar radiation warming an icy surface, but active heat. Internal heat. Heat from a source that is not the Sun. He noted that for 3I Atlas to appear bluer than the Sun, something about it must be hotter than the Sun's photosphere in terms of its emission spectrum or emitting through a process that preferentially generates blue light. The suggestion, never quite stated explicitly but hanging in the air like smoke, is that an internal power source could explain both the blue colour and the unexplained rapid brightening that accompanied it. A technological artifact with an engine, with systems generating waste heat, with emission profiles that have nothing to do with natural cometary processes, would look exactly like what we are seeing. Now, before anyone dismisses this as science fiction dressed up in academic language, consider what we actually know versus what we are assuming. We know 3I Atlas displays 9 documented anomalies, 9 properties that are unusual, unexpected, or unprecedented. The orbital alignment within 5 degrees of the ecliptic plane, the anti-tail pointing toward the Sun, the extreme velocity, the massive nucleus, the early onset of outgassing beyond Jupiter's orbit, the nickel without iron signature, the carbon dioxide dominance, the fine-tuned trajectory, and now this, the blue colour. Individually, each anomaly can be explained away. Statistical flukes happen, unusual compositions exist, nature is diverse and surprising. But 9 anomalies, 9 deviations from expected behaviour, all manifesting in the same object. At some point, the cumulative improbability starts to weigh on the mind. At some point, you have to ask whether we are looking at a very strange comet, or whether we are looking at something that is not a comet at all. The colour change also happened precisely when 3I Atlas was unobservable from Earth. This is not a conspiracy theory, it is simple geometry. As the comet swung around the far side of the Sun, it entered solar conjunction from our perspective. Too close to the Sun's glare for ground-based telescopes to track, hidden, invisible, and during those crucial days, during the exact window when it should have been at its most active, when solar heating should have been driving maximum outgassing, when we should have been able to see exactly what this object is made of and how it behaves, it was behind our star. The only eyes that could watch were the space-based solar observatories that happened to be looking in the right direction. Some have suggested this timing is suspicious, that an object following a trajectory fine-tuned to pass close to Mars, Venus and Jupiter, while remaining hidden from Earth, at its most revealing moment seems almost deliberately designed to frustrate observation. Others argue this is pure anthropocentric thinking, that the universe does not care about our viewing angles, and that we are simply unlucky in our geometry this time around. Both positions are reasonable. Both are impossible to prove or disprove. But the timing is, at minimum, frustrating. What happens next is crucial. 3I Atlas will emerge from behind the Sun in mid-November. Around the 11th, it should become visible again in the pre-dawn sky, low in the constellation Virgo. Amateur astronomers with 8-inch telescopes or larger should be able to pick it out, a faint fuzzy patch moving slowly against the background stars. But it will not be faint for long. If the brightening trend that surprised everyone at perihelion continues, if this object keeps defying predictions, it could emerge significantly brighter than the magnitude 12 to 13 currently estimated. And more importantly, it will still be blue, or it will have changed colour again, or it will have faded back to red, or it will display some completely new spectral signature that nobody has predicted. Every scenario tells us something different about what 3I Atlas actually is. A return to red would suggest that the blue phase was temporary, driven by specific conditions at perihelion that have now passed. Sustained blue would indicate an ongoing emission process that does not depend on solar distance. A shift to yet another colour, perhaps back to that September green, would point to complex chemistry evolving as the comet moves away from the Sun. But there is one scenario that nobody is discussing publicly, though it must be on some minds. What if 3I Atlas emerges from behind the Sun and it is dark? What if the brightening was not the beginning of increased activity but the end? What if something happened at perihelion, something we could not see, that fundamentally changed the object? Comets can fragment. Comets can undergo outbursts that expel huge amounts of material and then go quiet. Comets can, very rarely, simply disintegrate under the stress of solar heating. If 3I Atlas does not reappear as expected, if it emerges dim or not at all, the speculation will reach fever pitch. Some will say it broke apart, that the stresses of perihelion were too much for its structural integrity. Others will point to the non-gravitational acceleration that was detected, the thrust that suggested something was changing the object's trajectory, and ask whether it manoeuvred, whether it changed course, whether it did exactly what Loeb has been warning it might do. The December 19th Earth approach will answer these questions. When 3I Atlas comes within 270 million kilometres of our planet, when Hubble and Webb and dozens of ground-based telescopes all turn their full attention to this visitor from beyond, we will finally get the high-resolution data we need. We will see the true colour with precision. We will measure the spectral lines and identify exactly which molecules are present and in what ratios. We will determine whether that blue glow is still there, and if so, what is causing it. Until then, we are left with an impossible observation and inadequate explanations. We are left with a comet that glows bluer than the Sun it is orbiting. We are left wondering whether we are witnessing exotic natural chemistry from an ancient alien star system, or whether we are seeing something else entirely, something that wants us to wonder. Acceleration without explanation. The numbers came from David Farnocchia at NASA's Jet Propulsion Laboratory. October 31st, 2025. A navigation engineer with a PhD in mathematics from the University of Pisa. Someone whose entire professional life revolves around calculating trajectories with precision, measured in meters, across distances of millions of kilometers. When Farnocchia files a report about non-gravitational acceleration, people pay attention. When that report concerns 3I Atlas, people start asking questions that have no comfortable answers. 135 kilometers per day squared. That is the radial component, the acceleration pushing away from the sun. 60 kilometers per day squared transverse, perpendicular to the sun's direction. These are not trivial forces. These are not measurement uncertainties or statistical noise hiding in the error bars. This is thrust. Real, measurable, directional thrust occurring at exactly 1.36 astronomical units from the sun, right at perihelion, right at the moment of closest approach when we could not see what was happening. Comets accelerate all the time. This needs to be stated clearly before the speculation spirals out of control. Every active comet in the solar system experiences non-gravitational forces. As ice sublimates on the sunward side, as gas jets erupt from the nucleus, the escaping material pushes back against the comet like a tiny rocket engine. It is called the rocket effect, and it is completely normal. Darryl Seligman from Michigan State made this point repeatedly in interviews after the report went public. Comets have non-gravitational accelerations all the time. It would be almost strange to imagine a comet without one. But here is what makes 3I Atlas different. The magnitude of the acceleration compared to the amount of visible outgassing, the timing of when it occurred, and most disturbingly what it implies about mass loss. Evilobe did the calculation that everyone else was thinking but hesitant to publish. If you want to produce 135 kilometers per day squared of acceleration through the rocket effect, through normal gas ejection from a sublimating surface, you need to be losing mass. A lot of mass. Momentum has to be conserved. Every kilogram of gas that shoots away from the comet at a few hundred meters per second imparts an equal and opposite momentum to the nucleus. For an object the size and estimated mass of 3I Atlas, generating that much thrust means losing approximately 10% of its total mass over the span of a month. 10%. Think about what that means. This is not a gentle dusting of ice crystals evaporating into space. This is catastrophic mass loss. This is the comet essentially blowing itself apart, ejecting billions of tons of material in a continuous hurricane of outgassing that should create a massive, brilliant, unmistakable cloud of gas and dust around the nucleus. A cloud that should be visible across the solar system. A cloud that every telescope should easily detect when 3I Atlas emerges back into view. Loeb stated his prediction clearly. We should see a dense cloud of gas around it in November and December. Not might see, not could see, should see. Because if the non-gravitational acceleration is being caused by natural cometary outgassing, then the laws of physics demand that cloud exists. It is not optional. It is not uncertain. Momentum conservation is not a suggestion. It is a fundamental law that governs every interaction in the universe, from colliding galaxies down to billiard balls on a table. So what happens if we do not see that cloud? This is the question nobody in the mainstream astronomical community wants to ask out loud, but it hangs over every discussion of 3I Atlas like a storm front moving in. If December arrives, if Hubble and Webb and the ground-based arrays all turn their instruments toward this object at its closest approach to Earth, and if they see a relatively modest coma, a normal-looking tail, outgassing rates consistent with a typical comet at that distance from the Sun, then the rocket effect cannot explain the acceleration. The math does not work. The physics does not work. Something else must be producing that thrust. Loeb offered an alternative, not as his preferred explanation, not as what he thinks is most likely, but as a hypothesis that must be considered given the implications if it is correct. The non-gravitational acceleration might be the technological signature of an internal engine. Those are his words, published in his analysis on October 31st, the same day Farnocchia's report went public. An internal engine, a propulsion system, a device purpose built to change velocity, to alter trajectory, to maneuver. The immediate counterargument is that one data point does not make a pattern. Non-gravitational acceleration has only been detected at perihelion. We do not have tracking data showing sustained thrust over days or weeks. We do not have evidence of course corrections or trajectory changes beyond what natural forces can explain. We have one measurement, taken at one moment during a phase when we would expect maximum cometary activity anyway. Building an extraordinary hypothesis on such limited evidence is premature at best and irresponsible at worst. But here is the uncomfortable reality. We would not be able to detect sustained low-level thrust even if it was occurring. 3I Atlas is too far away, moving too fast, being tracked by too few observatories to measure subtle velocity changes in real time. The reason Fanokia could calculate the acceleration at all is because perihelion provides a known reference point. You can compare the predicted orbit, calculated from gravitational forces alone, to the observed position after perihelion and work backward to determine what additional forces must have acted. Outside of that window, the uncertainties are too large. The gaps in observation are too frequent. This is one of the most frustrating aspects of studying interstellar objects. They are here and gone. By the time we detect them, by the time we mobilize telescopes and coordinate observations and start gathering useful data, they're already well into their transit through the inner solar system. We get one chance, one pass, and if something happens during the weeks or days when we cannot observe them, when they are lost in the sun's glare or below the horizon, or simply too faint to track, we miss it. We are left with gaps in the data that speculation rushes to fill. The acceleration also occurred at the optimal moment for a maneuver. This is another detail that sounds conspiratorial until you understand the orbital mechanics. Perihelion is when a spacecraft would perform an Obeth maneuver, using the intense gravitational field close to the Sun to maximize the effectiveness of any thrust. Fire your engines at perihelion while moving at maximum velocity, and you get far more change in your final trajectory than firing those same engines anywhere else in the orbit. It is basic physics, taught in every astrodynamics course, used by every mission planner who wants to send a probe to the outer solar system efficiently. If 3I Atlas were artificial, if it were a probe or a spacecraft or whatever label you want to attach to a piece of technology from another civilization, perihelion is exactly when and where you would expect to see propulsive maneuvers. You would wait until you were hidden from Earth-based observation. You would wait until you were at the point of maximum gravitational assist. You would fire your engines then, when the fuel cost is lowest and the trajectory change is greatest and nobody is watching. Of course, that same logic works in reverse. If you are a natural comet experiencing maximum solar heating, perihelion is exactly when you would expect to see maximum outgassing and therefore maximum rocket effect acceleration. The timing proves nothing. It is consistent with both the mundane explanation and the extraordinary one. We are left in a state of uncomfortable ambiguity, knowing something happened but unable to determine what. There is also the matter of the acceleration's direction. 135 kilometers per day squared radially outward makes sense for a rocket effect. Gas erupting from the sunward side pushes the comet away from the sun. That is what we would expect. But 60 kilometers per day squared transverse? That is perpendicular to the sun direction. That is a sideways push, a lateral force, that does not naturally arise from simple symmetric outgassing. You would need asymmetric jets, active regions on the nucleus that are preferentially venting gas in specific directions, creating a net force that happens to be perpendicular to the sun's pull. Again, this is not impossible. Comet nuclei are not perfect spheres with uniform composition. They have valleys and ridges, areas where ice is more exposed, regions where dust layers insulate the interior. Sunlight hits these surfaces at different angles. Some areas sublimate faster than others. The resulting gas jets point in whatever direction the local topography dictates. If you have a jet erupting from the evening terminator, from the boundary between day and night on a rotating nucleus, it can produce exactly the kind of transverse acceleration we are seeing. But you need things to be arranged just right. The active regions need to be in the right places, the rotation needs to have the right orientation, the jets need to have the right strength ratios. It is possible, but it requires a very specific configuration of circumstances, whereas a propulsion system designed to change velocity would naturally produce thrust vectors that do not align with the sun's direction. You point your engines where you need to go, not where the sun happens to be. What makes this entire situation so maddening is that we have the technology to answer these questions definitively, but we cannot deploy it in time. A close flyby mission, a dedicated spacecraft sent to intercept 3I Atlas, would resolve everything instantly. Cameras would show us the nucleus directly. Spectrometers would measure the composition with precision. Particle detectors would sample the coma and tell us exactly what is being ejected and at what rates. We would know within hours whether the acceleration is consistent with natural outgassing or whether something else is happening. But there was no time to launch such a mission. 3I Atlas was discovered July 1st. Perihelion was October 29. 4 months is not enough time to design, build, test and launch a spacecraft, let alone have it reach its target. The mission proposals have been written. The engineering studies have been done. Multiple teams have shown that intercepts are feasible and affordable for future interstellar visitors. But for 3I Atlas, we are limited to remote observation. We are watching from hundreds of millions of kilometers away, trying to infer internal processes from faint photons collected by telescopes. The ESA's JUICE spacecraft will provide some data when it makes its observations between November 2nd and November 25th. Those instruments will see 3I Atlas in the immediate aftermath of perihelion, during the window when any massive outgassing should still be creating a huge detectable coma. But the data will not reach Earth until February 2026. The spacecraft is too far from Earth, the data rate is too slow, the queue of scientific observations is too long. We wait, we speculate, we wonder. And in the meantime, 3I Atlas is doing whatever it is doing, unseen and unmonitored, as it arcs away from the Sun and back out toward the darkness from which it came. If it is a comet, it is losing mass, creating that debris cloud, behaving exactly as natural processes demand. If it is something else, if those 9 anomalies are not coincidences but signatures, then it might be adjusting its course, changing its velocity, preparing for whatever comes next in a journey that started billions of years ago in a star system we will never see. December 19th will tell us which of these possibilities is closer to the truth. Until then, we have 135 kilometers per day squared of thrust, and no consensus explanation for where it came from. The missing Mars images. October 2nd, 2025. 3I Atlas passed within 30 million kilometers of Mars. For scale, that is closer than Mars has ever come to Earth in human history. It is close enough that spacecraft orbiting the red planet had their best opportunity to observe an interstellar visitor since we started putting machines around other worlds. And according to multiple sources, according to the geometry of the flyby and the capabilities of the instruments available, one particular camera had a perfect shot. HiRISE, the high-resolution imaging science experiment aboard NASA's Mars Reconnaissance Orbiter, a camera that can resolve features 30 centimeters across from an altitude of 300 kilometers above the Martian surface. A camera that has photographed avalanches mid-collapse, dust devils casting shadows, the parachutes and landing platforms of rovers that touched down decades ago. A camera that, when pointed at an object 30 million kilometers away, could achieve a pixel resolution of approximately 30 kilometers. That might not sound impressive until you remember that our best images of 3I Atlas from Hubble and Keck had resolutions 3 times worse. Those images were taken. Multiple researchers have confirmed that HiRISE was tasked with observing 3I Atlas during the Mars flyby window. The geometry was favourable, the pointing was possible, the observation was executed, and then the images disappeared into the bureaucratic void created by a government shutdown that began October 1st and lasted for weeks. Avi Loeb has been explicit about this. In his appearance on the Joe Rogan Experience, in his written statements, in interviews with multiple news outlets, he has stated clearly that he requested access to those images. He reached out directly to the principal investigator of HiRISE. He received no response. He followed up. Still nothing. The images exist. They are sitting on a server somewhere in NASA's data pipeline. But they have not been released. They have not been made public. They have not been shared with the scientific community that desperately wants to see them. NASA has not confirmed the existence of these images. They have also not denied it. They have said nothing. The silence is deafening. Now, before this descends into conspiracy territory, we need to understand what actually happened during that shutdown. On October 1st, the United States government ran out of funding authorization. Various agencies, including NASA, were forced to furlough non-essential personnel. Scientific operations continued where possible, but communications shut down. Press releases stopped. Data sharing slowed to a crawl. The public-facing infrastructure that normally makes NASA observations immediately available went dark. This was not unprecedented. Government shutdowns have happened before. They disrupt science every time. Observations get delayed. Data releases get postponed. The machinery of publicly funded research grinds to a halt, not because anyone decided to hide anything, but because the people who process and release that data are sitting at home, unpaid, waiting for Congress to figure out a budget. It is bureaucracy, not conspiracy. It is institutional dysfunction, not deliberate obfuscation. But the timing is what gnaws at people. 3i Atlas makes its closest approach to any planet during its entire transit through the solar system. The one moment when we could get high-resolution images from a vantage point we will never have again. And at that exact moment, the system for sharing those images shuts down. The coincidence feels almost deliberate, even though we know it is not. We know the shutdown had nothing to do with 3i Atlas. We know the budget impasse was about domestic policy and political manoeuvring that had been building for months. But still, the timing. Loeb called it terrestrial stupidity. Not evidence of aliens, not a cover-up, but basic human incompetence getting in the way of discovery. The universe does not care about government shutdowns, he said. Science does not pause because politicians cannot agree on spending bills. And when you have a once-in-a-lifetime opportunity to observe an interstellar object at close range, losing that opportunity to bureaucratic paralysis is inexcusable. Florida Congresswoman Anna Paulina Luna apparently agrees. Reports indicate she has been working to secure the release of those high-res images, using whatever political leverage is available to push NASA toward transparency. Whether this is genuine concern for scientific progress or opportunistic grandstanding is unclear. What matters is that someone with actual authority is asking the same questions that astronomers have been asking since October. Where are the images? When will they be released? What are they waiting for? The European Space Agency did release images. ESA's Mars Express and ExoMars Trace Gas Orbiter both observed 3i Atlas during the October 1st through October 7th window. The ExoMars TGO image shows the comet as a faint fuzzy dot, barely distinguishable from background stars, captured while the spacecraft's camera was tracking the fast-moving target. Background stars appear as streaks. The comet appears stationary. It is an impressive feat of pointing and tracking, but it tells us almost nothing about the object itself. No resolved nucleus, no detailed coma structure. Just confirmation that yes, 3i Atlas was where we predicted it would be, and yes, it looks vaguely comet-like from 30 million kilometers away. NASA's Mars rovers and the Mars Reconnaissance Orbiter were also supposed to observe the flyby. NASA confirmed this ahead of time. Curiosity, Perseverance, and MRO would all attempt to capture images during the optimal window, and then the shutdown happened and the flow of information stopped. We do not know if Curiosity saw anything. We do not know if Perseverance pointed its cameras skyward. We do not know what MRO captured beyond the high-rise observations that supposedly exist but remain unreleased. China's Tianwen-1 orbiter also should have had a view. With over 14,000 published images of Mars and its surroundings, the Chinese space program is not shy about releasing spectacular data when they have it. But there has been no statement from the China National Space Administration. No images, no press releases, no indication that they observed 3i Atlas at all. Some have suggested this silence is more concerning than NASA's because it is voluntary, not the result of a shutdown. If the images showed something ordinary, something perfectly consistent with a natural comet, why would China hesitate to publish them? Why would they pass up an opportunity to demonstrate their observational capabilities? The answer might be as simple as data processing delays. Space agencies routinely take weeks or months to calibrate and validate their observations before public release. Raw data fresh off the spacecraft looks nothing like the polished images that appear in press releases. Detectors have noise, cameras have artifacts, cosmic rays create false signals. Every frame needs to be checked, cleaned, analysed. The fact that we have not seen Chinese images yet does not necessarily mean anything suspicious is happening. It might just mean they are being thorough. But the absence of information creates a vacuum that speculation rushes to fill. Reddit threads dissect the timeline. YouTuber videos draw connections between the shutdown, the missing images, and Loeb's warnings about 3i Atlas. TikTok explainers claim the object went dark or changed course, or is somehow being hidden from public view by coordinated government action. None of this is supported by evidence. All of it is unfalsifiable, because the data that would settle the question has not been released. This is the frustrating reality of doing science in the modern era when the objects of study are also matters of intense public interest. Transparency is expected, demanded even. When data does not appear immediately, when there are gaps in the information flow, people assume the worst. They assume cover-ups and conspiracies and deliberate obfuscation. Sometimes they are right. More often they are wrong. But without the data, without the images, without the confirmation that yes, this is what 3I Atlas looked like from Mars orbit on October 2nd, we cannot separate reasonable skepticism from paranoid fantasy. What would those high-rise images actually show us? If they exist, if they are eventually released, what would we learn? The resolution is good enough to potentially see the nucleus directly, to measure its size with real precision, rather than relying on the wide error bars that currently place the diameter anywhere from 440 meters to 5.6 kilometers. We would see the coma structure, the distribution of gas and dust around the nucleus, whether it is symmetric or shows jets and active regions. We would get color data that could help identify the composition of the material being ejected. Most importantly, we would see whether the object looks normal, whether it has the fuzzy, irregular, obviously icy appearance of every comet we have ever examined up close, or whether it has sharp edges, geometric features, surfaces that reflect light in ways that ice and rock do not. High-rise would not be able to resolve fine details at that distance, but it could distinguish between a natural body and something artificial. It could give us a definitive answer to the question that Loeb keeps raising, and that most scientists keep dismissing. The fact that we do not have those answers yet is maddening. The fact that the images are sitting in a database somewhere, already captured, already transmitted back to Earth, but inaccessible because of political dysfunction or bureaucratic caution, or simple neglect is almost worse than if the observations had never been attempted. We were so close. 30 million kilometers is nothing in astronomical terms. We had the tools, we had the opportunity, and we let it slip through our fingers. Loeb has framed this as a failure of scientific culture. We are too reactive, he argues, too willing to wait and see rather than preparing in advance. 3I Atlas was discovered in July. By late July it was clear this object was coming close to Mars in October. There were months to coordinate observations, to ensure every available instrument was pointed at the target, to guarantee that data would flow smoothly regardless of political circumstances. Instead, we relied on normal procedures, on the assumption that everything would work as it always does. And when it did not, we lost data we will never get back. The shutdown ended. NASA resumed operations. The data archive was quietly restored. But there has been no announcement about the high-rise images, no statement about when or if they will be released, no explanation for the communication gap. The episode has left a lingering distrust, a sense that even if nothing nefarious happened, the system is too fragile to handle the kind of rapid response that interstellar visitors demand. Meanwhile, 3I Atlas continues its journey, unaware and unconcerned with the political dramas and institutional failures that prevent us from studying it properly. By the time the images are released, if they ever are, the comet will be far from Mars, moving into a different phase of its solar transit. The moment will have passed, the opportunity will be gone, and we will be left wondering what we might have seen if we had simply been better organized, better prepared, more committed to the principle that scientific data belongs to everyone and should be shared immediately, not hoarded behind bureaucratic walls. December will bring new opportunities. Hubble and Webb will observe from Earth orbit. Ground-based telescopes will track the object during its closest approach. We will get more data, better data, data that is not trapped in the maze of a government shutdown. But we will never get another Mars flyby. We will never get another chance at those 30-kilometer resolution images. Whatever they show, whatever they might have told us, that knowledge may be permanently out of reach. And that, more than any conspiracy theory or cover-up allegation, is the real tragedy of the missing Mars images. 9 anomalies and counting. When you study the universe professionally, you develop an instinct for what is normal and what is not. A comet with a slightly unusual orbit? Normal. A comet that outgasses earlier than expected? Unusual but not alarming. A comet that displays one genuinely puzzling characteristic? Interesting enough for a research paper, but 9 separate properties that each individually strain the boundaries of what we've observed before? That is when pattern recognition starts screaming that something fundamental is different about this object. Let us go through them systematically, not as a list of conspiracy fuel, but as an honest accounting of what makes 3I Atlas so persistently strange. Anomaly 1. The orbital alignment. 3I Atlas travels along a trajectory that is inclined only 5 degrees from the ecliptic plane, the disk containing all the major planets. For an object arriving from interstellar space, from a random direction in the galaxy, this is statistically improbable. The calculation has been done by multiple independent researchers. The odds of an interstellar object naturally arriving with this alignment are approximately 1 in 500, 0.2%. Not impossible, but not expected. Why does this matter? Because the ecliptic plane is where all the planets are. If you wanted to visit multiple worlds in one pass through a solar system, if you wanted to maximize your chances of close approaches to interesting targets, you would approach along the ecliptic. You would not come in at a steep angle that takes you far above or below the planetary disk. 3I Atlas passes near Mars, will pass near Venus, will pass near Jupiter. Its trajectory gives it access to the inner solar system's most significant bodies. By coincidence or design, it chose the optimal path. Anomaly 2. The anti-tail. Observed clearly in Hubble images from July and in ground-based telescopes through August, 3I Atlas displayed an extension of scattered light pointing toward the Sun, not away from it. Comets normally have tails that point away from the Sun, pushed outward by radiation pressure and the solar wind. Anti-tails are not unheard of. They occur when viewing geometry and particle dynamics create an optical illusion that makes part of the debris trail appear to point sunward. But the persistence of the anti-tail in 3I Atlas, its prominence in multiple observations, suggests something more than simple geometry. It suggests a physical process that is projecting material in an unusual direction. Loeb has proposed that this could be interpreted as thrust exhaust, as emissions from some kind of propulsion system visible during specific viewing angles. The mainstream interpretation is that it is a combination of large dust particles following different orbits than the nucleus, creating a fan of material that happens to appear sunward from our perspective. Both explanations are consistent with what we see. Neither can be proven without closer observation. Anomaly 3. The velocity. 3I Atlas is moving faster than any other interstellar object we have measured. At discovery, it was travelling at approximately 61 km per second relative to the solar system's centre of mass. For comparison, 1I Oumuamua was moving at 26 km per second, 2I Borisov at 32. 3I Atlas is nearly double the speed of the first interstellar visitor. This suggests it has been travelling for a very long time, accelerated by gravitational slingshots around multiple stars, building up momentum over billions of years. Or it suggests it departed its origin system with a high initial velocity, propelled by something other than gravity alone. Higher velocity also means the object has visited more star systems, encountered more stellar environments, been exposed to more cosmic radiation over its journey. An object moving this fast is not making its first pass through a solar system. It is an ancient traveller, and its composition should reflect that history. Whether it does is something we are still trying to determine. Anomaly 4. The massive nucleus. Current estimates place the diameter between 440 metres and 5.6 kilometres. The uncertainty is enormous, but even the lower bound makes 3I Atlas larger than 1I Oumuamua by a significant margin. The upper bound makes it genuinely huge, a mountain of ice and rock drifting through interstellar space. Large comets are rare in general. Large, interstellar comets should be extraordinarily rare because ejecting massive objects from planetary systems requires extreme dynamical events. The probability of detecting such an object during its brief transit through our solar system is correspondingly tiny. Yet here it is. Loeb has pointed out that if the nucleus is indeed on the larger end of the estimated range, if it is 5 or 6 kilometres across, then it cannot have originated from the typical reservoir of interstellar ice. The mass density of large bodies in the space between stars is simply too low. We would never detect one in a human lifetime. For 3I Atlas to be this big and to be here now would require either impossible luck or a different origin story than what we're assuming. Anomaly 5. Early outgassing. The comet became active far beyond Jupiter's orbit, at approximately 6.4 astronomical units from the Sun. Most solar system comets do not start outgassing until they are well inside Jupiter's orbit, typically closer than 5 AU. The reason is straightforward thermodynamics. Ice needs to reach a certain temperature before it sublimates rapidly enough to create a visible coma. Carbon dioxide ice, the dominant volatile in 3I Atlas, does sublimate more easily than water ice, which explains some of the early activity. But the intensity of the outgassing, the brightness it achieved while still so distant, suggests a composition or structure that is unusually responsive to weak solar heating. Anomaly 6. The nickel without iron signature. This is perhaps the most chemically bizarre property. Spectroscopic observations from the Keck telescope and the Very Large Telescope clearly showed emission lines from nickel atoms in the coma. Strong emission, prominent emission, but no corresponding iron lines. In natural astrophysical contexts, nickel and iron are almost always found together. They are synthesized together in stellar cores. They condense together in planetary nebulae. They travel together through the interstellar medium. When you see nickel, you see iron. Always. Except in 3I Atlas, and except in one other context. Industrially manufactured nickel alloys produced through the carbonyl process, where nickel tetracarbonyl is formed and then decomposed to yield pure nickel metal. This is a technique developed in the 19th century for refining nickel. It is not a natural process. It does not occur spontaneously in space. Yet 3I Atlas is emitting nickel in a ratio to other elements that matches industrial refining, not cosmic chemistry. The standard rebuttal is that we simply have not detected the iron yet, that the emission lines are too faint or being masked by other spectral features, that future observations with better sensitivity will reveal iron in the expected proportions, and this anomaly will evaporate. Maybe. But multiple independent observations have now failed to detect iron. At some point, non-detection becomes a detection of absence. Anomaly 7. Carbon dioxide dominance. 87% of the observed volatile emissions are carbon dioxide, 9% are carbon monoxide, only 4% is water. For a comet formed in the outer reaches of a typical planetary system, this ratio is backwards. Water ice is usually the most abundant volatile. Carbon dioxide is a minor component. The fact that 3I Atlas is so heavily enriched in carbon dioxide suggests it formed in a very cold environment, perhaps in the outer regions of its origin star system where temperatures were low enough that carbon dioxide remained frozen, while water had already been stripped away. Or it suggests a very old object, one that has been losing its more volatile components over billions of years, gradually becoming enriched in the less volatile species that remain. This also affects its behavior as it approaches the sun. Carbon dioxide sublimating creates a cooling effect that suppresses water ice evaporation. This might explain why the rapid brightening at perihelion caught everyone by surprise. The carbon dioxide outgassing dominated until the comet got close enough that water ice finally started sublimating in large quantities, creating a burst of activity that was not predicted by models based on normal cometary compositions. Anomaly 8. The fine-tuned trajectory. This is less about a single measurement and more about the cumulative geometric coincidences. 3I Atlas arrives aligned with the ecliptic plane. It passes within tens of millions of kilometers of Mars at a moment when multiple spacecraft are orbiting the planet. It will pass near Venus in early November. It will pass near Jupiter in March. Its perihelion occurs when it is geometrically hidden from Earth-based observation, behind the Sun, observable only by space-based solar monitors. Each of these facts individually is unremarkable. Taken together, they create a trajectory that seems optimized for planetary encounters, while minimizing scrutiny from the most capable observation platform in the solar system, which is Earth. Coincidence? Almost certainly. But the alignment of so many geometric factors in one object is the kind of thing that makes Loeb calculate probabilities and publish papers suggesting we should not dismiss low probability explanations out of hand when the consequences of being wrong are significant. Anomaly 9. The blue colour shift at perihelion. We covered this already, but it belongs in this catalogue because it is the most recent addition to the list, the most unexpected, the most difficult to explain through conventional cometary chemistry, and the one that might, if it persists when 3I Atlas comes back into view, finally push the mainstream scientific community to acknowledge that this object is not just unusual, but genuinely anomalous in ways that demand new physics or new chemistry to understand. 9 anomalies, 9 ways in which 3I Atlas deviates from the expected behaviour of interstellar comets. Loeb has assigned the object a score of 4 out of 10 on his scale of potential technological origin. 4 out of 10 is not certainty, it is not even a majority probability, but it is high enough to warrant serious attention, high enough that dismissing the possibility without thorough investigation would be scientifically negligent. The counter-argument, the one that most astronomers make when pressed on this topic, is that space is diverse. Comets come in endless varieties. Every object we observe closely reveals properties we did not expect. 1I Oumuamua was bizarre. 2I Borisov was surprisingly normal, but still had unique characteristics. 3I Atlas is just another data point in the wide distribution of possible cometary properties. If we observed 100 interstellar comets, we would see 100 different combinations of weird features. The fact that 3I Atlas has 9 anomalies just means it is on the far end of the distribution, not that it is outside the distribution entirely. This is a reasonable position. It is the conservative scientific stance. It is what you say when you want to avoid making extraordinary claims based on limited data. But it also requires accepting a lot of coincidences. It requires believing that 0.2% probabilities happen, that industrial refining chemistry occurs naturally in ways we have never observed, that trajectories optimize themselves for planetary encounters by pure chance, that objects happen to turn colours and accelerate and brighten in ways that have no good explanation but must be natural because the alternative is unthinkable. Maybe all of that is true. Maybe 3I Atlas is just profoundly unlucky in how many improbable things it happens to do simultaneously. Or maybe the simplest explanation, the one that requires the fewest separate coincidences, is that this object is not like the others, that it is not a comet in the traditional sense, that it is something we have not encountered before and do not yet have the conceptual framework to understand. Either way, the list is not closed. If 3I Atlas continues to surprise us, if new observations in November and December reveal additional anomalies, the count will keep rising, and at some point even the most conservative scientist will have to admit that calling something anomalous 9 times or 10 times or 11 times is just another way of saying we have no idea what we are looking at. The JUICE mission gamble. There is a spacecraft out there right now that has already seen what we're all waiting to discover. ESA's Jupiter Icy Moons Explorer, JUICE, made its observations of 3I Atlas between November 2nd and November 25th, 2025. Multiple instruments, cameras, spectrometers, particle sensors. The spacecraft was perfectly positioned to observe the comet in the immediate aftermath of perihelion during the critical window, when any massive outgassing from that unexplained acceleration should still be visible, still creating a bright expanding cloud of debris that would be unmistakable in the data. JUICE saw it. Whatever is happening with 3I Atlas right now, whatever state it is in as it moves away from the sun, JUICE has already captured that information. The photons have already hit the detectors, the data has already been recorded, the observations are complete, and we will not know what they show until February 2026. 3 months. 3 months of waiting while the most important data about 3I Atlas sits in a computer memory, aboard a spacecraft that is too far from Earth to send that data home quickly. 3 months of speculation, debate, analysis of older observations, and growing frustration among astronomers who know that the answers they need are already collected but utterly inaccessible. This is the reality of deep space missions. This is the price we pay for sending instruments to the outer solar system, where communication is slow and bandwidth is precious. Let me explain why JUICE's observations matter so much, why they are potentially more valuable than anything Hubble or Webb or ground-based telescopes will collect in December. It is all about timing and vantage point. When 3I Atlas went behind the sun from Earth's perspective, it did not go behind the sun from JUICE's perspective. The spacecraft is on a completely different trajectory, currently performing gravitational assists as it makes its way toward the Jupiter system. From JUICE's location, 3I Atlas remained visible throughout perihelion, and more importantly, JUICE was looking at the comet during the days and weeks immediately after perihelion, when solar heating was still intense, when any outgassing should have been at or near its maximum, when the acceleration detected by phonokia would have been creating observable effects. If Loeb's prediction is correct, if the non-gravitational acceleration requires 10% mass loss to be explained by natural rocket effects, then JUICE should have seen a massive coma, an enormous cloud of gas and dust, far larger and brighter than anything observed before perihelion. The particle sensors would have detected elevated densities of ions and neutrals. The spectrometers would have measured the composition and temperature of the outflowing material. The cameras would have imaged the coma structure, showing whether the emissions are symmetric or coming from active jets on specific parts of the nucleus. All of that data exists, right now, stored in JUICE's memory, waiting to be transmitted. The reason for the delay is not mysterious or suspicious, it is purely technical. JUICE is currently about 2 astronomical units from Earth and moving farther away. At that distance, radio signals take approximately 16 minutes to travel one way. The spacecraft uses its main high-gain antenna as a heat shield during certain parts of its trajectory, which means it has to rely on the smaller medium-gain antenna for communications. The medium-gain antenna has a much lower data rate. Everything slows down. Science data gets prioritized and queued. Observations are transmitted in the order they were taken, with the most time-critical information sent first. The 3I Atlas observations, as scientifically interesting as they are not the primary mission objective. JUICE was designed to study Jupiter's icy moons, Europa, Ganymede, Callisto. That is where the major science return will come from, and that is what the mission operations team is focused on. The comet observations were a bonus, an opportunity target, something the spacecraft could look at because it happened to be in the right place at the right time. But they are not driving the data transmission schedule, so we wait. We wait while JUICE continues its journey. We wait while the data slowly trickles back to Earth at kilobits per second. We wait while 3I Atlas grows dimmer and more distant, while the opportunity to coordinate JUICE's findings with contemporaneous Earth-based observations slips away. This is maddening for researchers who want to know now, who need to know now, who are planning December observation campaigns without knowing what JUICE has already discovered. Should they focus on measuring coma density, trying to detect that predicted massive gas cloud? Or has JUICE already determined that no such cloud exists, making those measurements a waste of precious telescope time? Should they prioritize spectroscopy, searching for emission lines that might explain the blue color? Or has JUICE already identified the source, making further spectral work redundant? Without the JUICE data, astronomers are working blind. They are planning observations based on incomplete information, on predictions that might already be proven wrong, on questions that might already have answers. It is not an efficient way to do science. But it is the reality of the situation. JUICE is not going to suddenly download terabytes of data because the astronomy community is impatient. The spacecraft follows its timeline. The data arrives when it arrives. We adapt. There is also the question of what JUICE can actually resolve at the distance it was observing from. The closest approach between JUICE and 3I Atlas occurred on November 4th, when the separation was approximately 64 million kilometers. For scale, that is about 40% of the distance between Earth and the Sun. From that range, even JUICE's capable instruments cannot see fine details on the nucleus. The Janus Visible Light Imager has good resolution, but not good enough to distinguish surface features from tens of millions of kilometers away. What JUICE can do is measure the overall brightness, the size and shape of the coma, the distribution of material around the nucleus. The MAGIS infrared spectrometer can identify molecules based on their absorption and emission lines, determining what kinds of ice and gas are present. The SWI submillimeter wave instrument can detect specific molecular species that are difficult to observe at other wavelengths. The particle sensors can directly sample any gas or dust that happens to be in the spacecraft's vicinity, though at 64 million kilometers, the density of cometary material is probably too low to produce significant counts. Still, the combination of all these instruments operating simultaneously, looking at the same target from the same vantage point, will provide a dataset that no single ground-based telescope can match. Simultaneous multi-wavelength observations are incredibly powerful for constraining physical models. When you see the same feature in visible light, infrared, and submillimeter simultaneously, you can determine the temperature, composition, and dynamics of the emitting material with far greater certainty than if you have to piece together observations taken at different times from different locations. NASA's Europa Clipper mission was also supposed to coordinate observations with JUICE. Both spacecraft carry ultraviolet spectrographs designed to study tenuous atmospheres and exospheres around icy moons. Those same instruments can be pointed at comets. The idea was that simultaneous UV observations from two different spacecraft could provide stereoscopic views of the coma, revealing three-dimensional structure that single-point observations cannot capture. Whether that coordination actually happened, whether Europa Clipper successfully targeted 3I Atlas during the observation window is unclear. No announcements have been made, no preliminary results have been shared. We are left to wonder and wait. February 2026 feels like an eternity from now. By then, 3I Atlas will have made its closest approach to Earth. The December observations will be complete. Hubble and Webb will have obtained their data. Ground-based campaigns will have finished. The scientific community will have formed preliminary conclusions based on everything except the JUICE observations. And then, 3 months late, the JUICE data will arrive, and it might confirm everything we think we know. Or it might upend the entire interpretation, revealing that what we thought was happening at perihelion was nothing like what actually occurred. This is the gamble. This is the frustration of studying transient phenomena with slow communication systems. We are forced to make decisions, to plan observations, to publish papers, without access to data that already exists, but cannot be retrieved quickly enough to influence those decisions. It is like trying to solve a puzzle while someone holds back random pieces, promising to give them to you eventually, but not right now, not when you actually need them. Some have suggested that ESA should reprioritize the data transmission, that 3I Atlas is important, enough to warrant moving its observations to the front of the queue. But that is not how mission operations work. You cannot just rewrite the entire data management plan because one target turns out to be more interesting than expected. There are contractual obligations to instrument teams, predetermined schedules for different science objectives, bandwidth allocations that were decided years ago during mission planning. Changing all of that on the fly would create chaos, would jeopardize other science, would require approvals from multiple levels of ESA hierarchy. It is not going to happen. The data will arrive when the schedule says it will arrive. We will see it in February. Until then, we are on our own. What makes this situation even more complex is that JUICE's observations might be the only reliable measurement of 3I Atlas in its immediate post-perihelion state. By the time the comet emerges back into view from Earth in mid-November, by the time telescopes can track it again, several weeks will have passed since perihelion. If the object underwent rapid changes at closest approach, if it brightened dramatically and then faded, if it released a burst of gas that then dissipated, we will have missed it. The only record of that critical transition will be in JUICE's data, and if that data contradicts what ground-based telescopes see in late November and December, if the comet appears different from what JUICE observed just weeks earlier, we will be left trying to explain not just one set of anomalies, but two. The December 19th Earth approach will still be valuable. It will still provide high-resolution images, detailed spectra, precise photometry, but it will be observing a comet that has been away from perihelion for nearly 2 months. A comet that has cooled down, slowed its outgassing, potentially changed its appearance and behaviour. We will be seeing 3I Atlas in a different state than JUICE saw it. Comparing the two datasets will require careful modelling, assumptions about how comets evolve as they move away from the Sun, extrapolations that introduce uncertainty. If only we could see the JUICE data now. If only we could know what 3I Atlas looked like in early November, we could plan the December observations so much more effectively. We could target specific features, confirm or refute specific hypotheses, use our limited telescope time on questions that actually matter, rather than fishing blindly for answers. But we cannot. So we wait, we speculate, we prepare for December without knowing what JUICE has already revealed. And we hope that when February finally arrives, when the data finally reaches Earth, it will have been worth the wait. That it will answer the questions we have been asking for months. That it will finally tell us whether 3I Atlas is an exceptionally strange comet or something else entirely. 3 months. It is not that long in the grand scheme of a multi-year space mission, but right now, with 3I Atlas dominating headlines and sparking debates, and keeping astronomers awake at night wondering what they are looking at, 3 months feels like forever. Loeb versus the world. The fight is not really about 3I Atlas. It is about how science should respond to anomalies, how much weight to give to improbable explanations, and whether the possibility of discovering something truly revolutionary justifies the reputational risk of being spectacularly wrong. Avi Loeb has made his position clear. When you encounter an object with 9 unexplained properties, when the cumulative probability of all those anomalies occurring naturally drops below a certain threshold, you have a scientific obligation to consider alternatives, even uncomfortable alternatives, even alternatives that sound like science fiction. The mainstream astronomical community disagrees, loudly. Brian Cox, physicist and science communicator, stated it plainly. 3I Atlas is a comet made of carbon dioxide and water ices and bits of other stuff. It has a predictable orbit. It will pass the sun and continue drifting through the galaxy. The speculation about alien origins is, in his words, drivel. It is sensationalism. It is misleading the public about how science works and what the evidence actually shows. Loeb's response was equally blunt. Cox is like a cave dweller who finds a phone and calls it just a rock. Real scientists play on the field guided by data while commentators sit on the sidelines repeating popularity. The implication is clear. Cox is not doing science. He is performing for an audience. He is taking the safe position, the one that will not generate controversy or ridicule, the one that allows him to maintain his status as a trusted voice of scientific authority. But safe positions do not lead to discoveries. They lead to confirmation of what we already believe. This divide, this fundamental disagreement about scientific methodology and risk tolerance, has become the subtext of every discussion about 3I Atlas. It is not really about whether the comet is natural or artificial. It is about whether we should even be asking that question out loud. Tom Statler from NASA represents the institutional position. It looks like a comet. It does comet things. It very strongly resembles the comets we know. Yes, it has some properties that are unusual. Yes, it behaves slightly differently from solar system comets. But the evidence overwhelmingly points to a natural origin. To suggest otherwise based on the limited data we have is premature and irresponsible. It creates false uncertainty in the public mind. It damages the credibility of the scientific enterprise. Loeb has heard all of this before. He heard it when he suggested that One-Eye Oumuamua might be artificial. He heard it when he published his hypothesis about light sails and interstellar probes. He heard it when he founded the Galileo project to search for technological signatures in astronomical data. The criticism has been consistent. You're being too speculative. You're not being rigorous. You're chasing headlines instead of doing proper science. You're undermining public trust by entertaining ideas that have no solid evidentiary foundation. But here is the problem with that criticism. Loeb is not ignoring the evidence. He is not making things up. He is looking at the same data as everyone else and arriving at a different conclusion about what deserves attention. He's assigning higher weight to the anomalies, lower weight to the standard explanations, and calculating that the probability space for exotic hypotheses is larger than most of his colleagues believe. That is not unscientific. That's a different approach to Bayesian reasoning about uncertain evidence. Consider the nickel without iron signature. The standard explanation is that iron is present but we have not detected it yet, that future observations will find it. This is a reasonable hypothesis. It is conservative. It does not require new physics or new chemistry. But it is also unfalsifiable in the near term. You can keep saying we just have not looked hard enough every time a new observation fails to find iron. At what point do you accept that maybe, just maybe, the absence of iron is real, and the chemistry of 3I Atlas is genuinely different from anything we have seen before? Loeb's answer is that we should be taking the observations at face value. If multiple independent spectrographs on multiple instruments have failed to detect iron, we should consider the possibility that there is no iron to detect. And if there is no iron, if nickel is being emitted without its usual companion element, then we need an explanation for why. The carbonyl refining process is one explanation. It happens to be an industrial process, one associated with technological manufacturing. That does not mean 3I Atlas is artificial, but it does mean we should not dismiss the possibility without further investigation. The scientific establishment has reflexive immune response to suggestions of alien technology. This is understandable. The field has been burned before by wild speculation that turned out to be wrong. Pulsars were briefly thought to be artificial beacons before we understood neutron stars. Fast radio bursts generated speculation about advanced civilizations before we found natural mechanisms that could produce them. The WOW signal, the face on Mars, the canals of Venus. Every time the extraordinary explanation turned out to be wrong. Every time natural phenomena were misinterpreted as something more. This history creates a bias. When someone like Loeb suggests that an interstellar object might be artificial, the immediate reaction is not to evaluate the claim on its merits, but to pattern match it to previous false alarms. It sounds like the face on Mars all over again. It sounds like someone desperate for attention making claims they cannot back up. It sounds like bad science. But that pattern matching can also be wrong. Just because previous claims of alien technology were incorrect does not mean all such claims are incorrect. The universe is under no obligation to follow our expectations. It is entirely possible that somewhere in the vast catalogue of astronomical phenomena there exists actual evidence of technology created by non-human intelligence. And if that evidence does exist, it will initially look anomalous. It will violate expectations. It will seem too unlikely to be true. The scientists who point it out will be criticised and ridiculed, accused of sensationalism and poor judgment, until enough data accumulates that the conclusion becomes unavoidable. Loeb argues that we are in that initial phase with 3I Atlas, that the anomalies are significant enough to warrant serious investigation, that assigning a 30 to 40% probability to non-natural origin is not wild speculation, but a reasonable assessment given the available evidence. That if we dismiss this possibility now, if we close off that line of inquiry because it makes us uncomfortable, we might be making the same mistake that scientists made when they dismissed continental drift, or when they rejected the existence of meteorites, or when they insisted that the universe was static and eternal. His critics argue that extraordinary claims require extraordinary evidence, and the evidence for 3I Atlas being anything other than a comet is not extraordinary. It is suggestive at best. The anomalies can all be explained through conventional physics. The fact that the explanations require several unlikely things to be true simultaneously does not mean we should abandon natural explanations in favour of unproven alternatives. Darryl Seligman from Michigan State falls into this camp. He has studied 3I Atlas extensively. He has published papers on its composition and trajectory, and he is confident that it is a comet. The non-gravitational acceleration is normal for comets. The nickel emission, while unusual, does not require exotic chemistry to explain. The orbital alignment is unlikely but not impossible. The velocity is high, but within the expected range for objects ejected from nearby star systems billions of years ago. Every single anomaly, when examined individually, has a plausible natural explanation. Loeb's response is that this misses the point. It is not about whether each anomaly can be explained individually. It is about whether the collection of anomalies taken together is more easily explained by one hypothesis versus another. And in his judgment, an artificial object would naturally display exactly the suite of properties we see in 3I Atlas. It would be aligned with the ecliptic to access multiple planets. It would have unusual chemistry because it is made of manufactured materials, not natural ices. It would show non-gravitational acceleration if it had propulsion systems. It would be large and fast if it was designed for interstellar travel. It would turn colours if internal systems were generating heat or emissions. None of this is proof. Loeb acknowledges this repeatedly. But he argues that proof is not the standard we should be applying at this stage. The standard should be whether the hypothesis is worth investigating, whether it deserves resources, attention, follow-up observations. And his answer is yes, emphatically yes. Because the consequences of being right are so enormous that even a 10% probability, even a 5% probability justifies the effort required to find out. The counter-argument is that chasing low-probability hypotheses is a waste of limited resources. Telescope time is precious. Funding is scarce. If we divert attention to unlikely explanations, we miss opportunities to study things we know are real and important, and we risk training the public to expect aliens around every corner, creating a boy who cried wolf scenario where genuine discoveries are met with skepticism because the field has been saturated with false positives. This is the impasse. Both sides have valid points. Both sides are arguing from positions that are defensible within the framework of scientific methodology. And both sides are deeply frustrated with each other because the disagreement is not really about data. It is about values. About what kind of risks are worth taking. About whether it is worse to miss a genuine discovery because you were too conservative, or to waste resources on speculation because you were too credulous. 3I Atlas has become the battleground for this larger conflict. Every new observation, every anomaly, every unexplained brightening or colour change gets interpreted through these opposing frameworks. Loeb sees evidence accumulating in favour of his hypothesis. His critics see confirmation that they were right to be sceptical, that the object is revealing itself to be natural after all, just unusually natural. December will not resolve this debate. No matter what the observations show, both sides will find ways to interpret the data in line with their priors. If the comet displays that predicted massive gas cloud, Loeb's critics will say, see, it is natural outgassing, exactly as we said. If the comet does not display that cloud, Loeb will say, see, the rocket effect cannot explain the acceleration. Something else is happening. The evidence will not be definitive because it never is. There will always be room for alternative interpretations, for additional hypotheses, for wait and see. The only thing that would definitively settle the question is close-up observation, a spacecraft mission to 3I Atlas, cameras that can resolve surface features, instruments that can sample the coma directly, maybe even a lander that could touch the surface and determine its composition and structure with absolute certainty. But that mission does not exist and cannot be launched in time. 3I Atlas will leave the solar system before we could reach it. So the debate continues, Loeb versus the world, and everyone watching, waiting to see who history will judge to have been right. The brightening that broke the models. Qicheng Zhang from Lowell Observatory and Carl Battams from the US Naval Research Laboratory have been tracking comets for years. They understand how comets brighten as they approach the sun. They know the equations, the physics, the empirical relationships that connect heliocentric distance to apparent magnitude. When a comet gets closer to the sun, it heats up. Ice sublimates faster. More gas and dust get released. The coma grows larger and brighter. It is predictable. It follows power laws. You can calculate what the brightness should be at any given distance if you know a few basic parameters about the comet's composition and size. 3I Atlas did not follow those rules. Between September and October 2025, as it plunged toward perihelion, it brightened at a rate that far exceeded every prediction. Not by a small margin. Not by the kind of variation you expect from comets that are slightly more active or slightly less dusty than average. By a factor that required adding extra terms to the equations. By an amount that suggested something fundamentally different was happening inside or around this object. The numbers tell the story. During the early part of its approach, 3I Atlas was brightening roughly as expected, following a power law where brightness increased proportionally to distance from the sun raised to some negative exponent. Typical comets show exponents around -3 or -4. As you get twice as close to the sun, you get somewhere between 8 and 16 times brighter. 3I Atlas was following something like that pattern through July and August. Observers could predict its magnitude a few weeks in advance with reasonable accuracy. Then, in September, something changed. The brightening accelerated. The data started deviating from the model predictions. And by early October, when space-based solar observatories could track the comet as it moved behind the sun from Earth's perspective, the brightening had become extreme. Zhang and Battams calculated that 3I Atlas was following a power law with an exponent of approximately -7.5 plus or -1. That is nearly double the rate of normal comets. It is brightening so rapidly that every day closer to the sun results in a dramatic increase in apparent magnitude. Why does this matter? Because brightness is not just about aesthetics. Brightness is a proxy for activity. When a comet gets brighter, it means more surface area is actively sublimating. More ice is turning to gas. More dust is being lifted off the nucleus. The total energy budget of the system is increasing, and that energy has to come from somewhere. For a normal comet, it comes from solar heating. Sunlight hits the surface, warms the ice, drives sublimation. The rate at which this happens depends on how much sunlight is being absorbed, which depends on distance from the sun. Twice as close means 4 times more solar energy per unit area. 4 times more energy means faster sublimation, but not 7.5 power law faster. Something else must be contributing. One possibility is that the comet underwent a compositional transition. Early in its approach, when it was farther from the sun, carbon dioxide ice was the dominant volatile. Carbon dioxide sublimates easily, even at low temperatures, which explains why 3I Atlas started outgassing beyond Jupiter's orbit. But carbon dioxide also has a cooling effect. As it evaporates, it absorbs heat from the surrounding material, lowering the surface temperature and suppressing the sublimation of other ices, particularly water. The hypothesis is that as 3I Atlas got closer to the sun, the carbon dioxide layers exhausted themselves or retreated beneath the surface, exposing water ice that had been protected until that moment. Water ice sublimates much more vigorously once it reaches the right temperature. The latent heat of sublimation is different. The vapor pressure curves are different. You can get a sudden burst of activity when water ice becomes the dominant volatile, a transition that would not show up gradually in the data, but rather as a sharp increase in brightening rate right around perihelion. This is a reasonable explanation. It fits the chemistry we know 3I Atlas has. It does not require new physics, but it also requires very specific conditions. The carbon dioxide layer needs to be thick enough to suppress water sublimation for months, but thin enough to erode away at just the right moment to create the observed brightening surge. The nucleus needs to have a layered structure with carbon dioxide on top and water underneath, which is the opposite of what you would expect if the comet formed in a cold environment where carbon dioxide should freeze first and water should be deeper in the interior. The alternative explanation, the one that Zhang and Battams carefully avoided stating explicitly, but which hangs in the air whenever this data is discussed, is that the brightening is not entirely due to sublimation, that some additional energy source is contributing, that something inside 3I Atlas is generating heat or releasing stored energy in a way that adds to the solar heating and creates a brightening curve that natural processes alone cannot reproduce. Loeb predictably has run with this idea. He pointed out that the blue colour observed at perihelion is consistent with emission from a source hotter than you would expect from passive solar heating. If 3I Atlas has an internal power source, if it is generating energy through some mechanism other than absorbing sunlight, that energy has to go somewhere. It would heat the surface, it would drive additional sublimation, it would make the comet brighter than predictions based on solar heating alone, and it would create spectral signatures, emission lines, colours that do not match what you get from reflected sunlight, passing through a cloud of dust and gas. The mainstream response is that this is unnecessary speculation, that adding an internal power source to explain the brightening requires assuming the existence of something we have no independent evidence for. That the compositional transition hypothesis, while requiring specific conditions, is still vastly more probable than the hypothesis that 3I Atlas contains an energy source of unknown origin. Occam's razor says we should prefer the simpler explanation, and the simpler explanation is that this is a comet with an unusual but natural composition behaving in an unusual but natural way. But Occam's razor is only useful if you define simplicity correctly. Is it simpler to assume a very specific layered structure with precise compositional boundaries that happen to produce a brightening surge at exactly the moment when the comet is unobservable from Earth? Or is it simpler to assume that an object with 9 other anomalies has a 10th anomaly that is mechanistically related to the first 9? The answer depends on what you already believe about 3I Atlas. If you're convinced it is a natural comet, then any natural explanation, no matter how contrived, is simpler than an artificial explanation. If you're open to the possibility that it is something else, then adding one more piece of evidence to that hypothesis is the simpler path. What makes the brightening especially puzzling is that we do not have a complete light curve. We have observations from before perihelion showing the acceleration of brightening. We have space-based observations from right at perihelion showing that the comet was extremely bright, bluer than the sun, emitting strongly in wavelengths that suggest gas rather than dust. But we do not have continuous observations showing whether the brightening peaked and then declined, or whether it plateaued, or whether it continued increasing even after perihelion when you would expect it to start fading. This gap in the data is maddening. If we could see the post-perihelion light curve, if we knew how quickly 3I Atlas faded or whether it faded at all, we could constrain the model significantly. A rapid decline would suggest that the brightening was a temporary outburst, maybe a large piece of the nucleus breaking off and creating a sudden surge of exposed ice that then quickly exhausted itself. A plateau would suggest sustained high activity, which is harder to explain with passive solar heating unless the nucleus is much larger than we think. A continued increase would be almost impossible to explain naturally and would strongly support the idea that something other than solar distance is controlling the brightness. JUICE might have this data. The spacecraft was observing during the critical window. It could have measured the brightness every day, tracking the evolution of the light curve through perihelion and into the post-perihelion phase. But we will not see that data until February, so we are left guessing, building models based on incomplete information, hoping that when the full picture finally emerges it will make sense of what we are seeing now. Amateur astronomers have been trying to fill the gap. Rachati Boonplod, a skilled comet hunter, spotted 3I Atlas in GOES 19 images on October 18th, and tracked it until October the 24th. His observations showed that the comet remained bright, comparable to nearby stars at magnitude 11, even as it moved away from perihelion. That is suggestive of sustained activity, not a brief outburst. But the observations are limited by the capabilities of a weather satellite's solar monitoring camera, which was not designed to do precision photometry on faint comets. The error bars are large, the calibration is uncertain. It is better than nothing, but it is not definitive. Ground-based observations will resume in mid-November, when 3I Atlas emerges from behind the Sun. Dozens of telescopes will measure its brightness, track how it changes over subsequent weeks, compare it to pre-perihelion data. If the comet is significantly brighter than it was in September, if it maintains a high level of activity even as it moves farther from the Sun and cools down, that will be a major clue about what happened at perihelion. If it has faded back to expected levels, if it now follows a normal power law decline, that will suggest the brightening was temporary, a phase transition or compositional quirk that has now passed. But there is a third possibility that nobody wants to consider openly. What if 3I Atlas does not brighten according to any power law, either normal or anomalous? What if its brightness varies in ways that do not correlate with solar distance at all? What if we see flares, sudden increases followed by declines, patterns that suggest internal processes rather than external heating? That would be the strongest evidence yet that something deeply unusual is happening with this object. That would push even skeptics to admit that 3I Atlas is not behaving like any comet we have ever studied. The brightening that broke the models is not just a scientific curiosity, it is a window into the internal workings of 3I Atlas. Every photon that reaches our telescopes carries information about where it came from, what created it, what processes are active on or inside the comet. When those photons arrive in quantities that violate our expectations, when they form a light curve that does not fit the equations, they are telling us that our understanding is incomplete. Either the comet's composition is stranger than we thought, or its structure is more complex than we assumed, or something else is providing energy beyond what the Sun delivers. December will give us more photons, more data points, a better light curve, and eventually we will understand why 3I Atlas brightened the way it did. We will build a model that fits the observations. We will publish papers explaining the physics and chemistry. But whether that explanation involves natural processes or something more exotic remains to be seen. For now, we have a comet that defied predictions, broke the models, and left us wondering what else it might do before it leaves the solar system forever. What the colour changes really mean red in July, green in September, blue in October, 3 different colours across 4 months, each representing a fundamentally different state of matter and energy in the coma of 3I Atlas. This is not normal. This is not how comets typically behave. Yes, comets can change colour as they approach the Sun, as different ices sublimate at different temperatures, as the balance between dust and gas shifts. But the progression we are seeing, the specific sequence of red to green to blue, tells a chemical story that does not quite make sense when you try to write it down. Let us start with red. When 3I Atlas was first observed in detail in July, when Hubble captured its image showing the peculiar anti-tail, the colour signature was reddish. Dust dominated. Sunlight reflecting off small particles, carbon-rich grains, organics that had been baked by cosmic radiation during billions of years of interstellar travel. This is what you expect from a comet that is still relatively cold, still far enough from the Sun that sublimation is just beginning, that the coma is mostly comprised of solid particles rather than gas. Red means dust. Red means passive reflection of sunlight. Red means business as usual. Then came the green phase. September 7th, during that total lunar eclipse, astrophotographers Michael Jaeger and Gerald Riemann captured images from Namibia that showed 3I Atlas glowing with a distinct green hue. Blue-green specifically, with the comet displaying a coma 2.5 arc minutes across, clearly visible in both blue and green filters. This is classic comet behaviour. Green means diatomic carbon, C2 molecules fluorescing under solar ultraviolet radiation. It is the signature of organic compounds breaking down, of complex carbon chains being shattered by sunlight and emitting that characteristic emerald glow as electrons cascade back to their ground state. Except there is a problem. Earlier spectroscopic observations from the Very Large Telescope and from Keck showed that 3I Atlas has unusually low levels of carbon chain molecules. The paper by Luis Salazar Manzano explicitly noted that 3I Atlas is among the most carbon chain depleted comets known. The ratio of cyanogen to C2 is extremely high, meaning there is very little of the molecule that normally produces green emission. So where was the green colour coming from? One possibility is that the spectroscopic observations were incomplete, that C2 was present but at levels too low to detect with the integration times and sensitivities available. Then, as the comet got closer to the Sun, as sublimation accelerated, enough C2 accumulated in the coma to produce visible green fluorescence. The molecule was always there, just hiding below the detection threshold until conditions became favourable. Another possibility is that the green was not from C2 at all. Other molecules can produce green emission under specific conditions. Certain nickel compounds, when excited by ultraviolet light, can fluoresce at wavelengths that appear greenish. Given that 3I Atlas is emitting nickel in unusual quantities, given that the nickel lacks its usual ion companion, maybe the green phase was not about carbon chemistry, but about metal chemistry. Maybe we were seeing the signature of nickel tetracarbonyl breaking down, releasing nickel atoms that then absorbed and re-emitted light in the green part of the spectrum. This is speculative. No one has measured nickel fluorescence from a comet before, because no comet has displayed prominent nickel emission before. We are in uncharted territory, trying to explain observations that do not fit existing frameworks. But if the green phase was related to nickel rather than carbon, that would connect it to the broader pattern of chemical anomalies. It would be one more piece of evidence that 3I Atlas has a composition unlike anything else we have studied. And then it turned blue, not just slightly blue, not blue-tinged, intensely, remarkably blue, bluer than the Sun. And this is where conventional explanations start to break down entirely. Blue emission from a comet is rare but not unheard of. Ionized carbon monoxide can fluoresce in blue wavelengths when hit by solar wind particles and ultraviolet radiation. The ion tail of a comet, the part that points directly away from the Sun driven by magnetic fields rather than radiation pressure, often has a blue colour because it is made of ionized molecules rather than neutral gas or dust. So seeing some blue in the spectrum of 3I Atlas would not be surprising. But this was not some blue. This was dominant blue. The colour observations from Stereo, from SOHO, from GOES 19 all showed that the coma was emitting more strongly in blue wavelengths than in red. For an object that should be cooler than the Sun, for an object that should have dust reddening its reflected light, for an object that should be producing emission primarily from molecules with characteristic wavelengths, in the ultraviolet, visible green, or near infrared, blue dominance is wrong. It suggests a thermal spectrum that is hotter than expected, or it suggests emission from a source that preferentially produces blue light through some process that is not simple fluorescence. The thermal interpretation runs into immediate problems. For 3I Atlas to have a thermal spectrum that peaks in the blue, it would need a surface or coma temperature of several thousand Kelvin. That is hotter than most stars. That is hotter than any natural object in the solar system except the Sun itself. You cannot heat ice to several thousand Kelvin with sunlight from 1.36 AU away. You cannot even heat rock to those temperatures at that distance. If the blue colour is thermal, if it is black-body radiation from a hot surface, then that heat must be coming from inside the object, not from solar heating alone. This brings us back to the question of internal energy sources. What could generate enough heat inside a comet to produce visible blue emission? Natural radioactive decay is far too weak. Even if 3I Atlas had an unreasonable concentration of uranium or thorium, the heat generation would be negligible compared to what is needed. Chemical reactions, the kind that could occur if the nucleus had pockets of volatile compounds that suddenly mixed and reacted, could generate heat. But sustaining that heat long enough to produce the observed emission, doing it in a way that creates blue dominance rather than a broad thermal spectrum, requires very specific conditions that seem contrived. The alternative, the one that Loeb has been hinting at without stating outright, is that the blue emission is not thermal at all, that it is line emission from some molecule or process we have not identified yet. That 3I Atlas is releasing energy through a mechanism that naturally produces blue photons, and we are seeing the signature of that mechanism in the colour data. What that mechanism might be, what kind of chemistry or physics could create such emission, without corresponding features in other parts of the spectrum, is unclear. We do not have a good natural candidate, or the emission is not natural. If 3I Atlas has internal systems, power generation, waste heat that needs to be radiated away, the colour of that radiation depends on the temperature of the radiating surface and the materials involved. Certain industrial processes, certain types of lighting, certain plasma states all produce characteristically blue emission. A spacecraft running on a nuclear reactor would have a thermal spectrum determined by the reactor's operating temperature. A probe using ion engines would create a blue glow from the ionized propellant. These are not astronomical phenomena, they are engineering phenomena. But if you are looking at an engineered object rather than a natural one, engineering phenomena are what you would expect to see. This is where the colour progression becomes particularly interesting. Red to green to blue is not a natural sequence based on temperature alone. If 3I Atlas was simply heating up as it approached the Sun, you would expect the colour to shift from red toward yellow, maybe eventually to white, as the thermal spectrum shifted to shorter wavelengths. You would not expect discrete phases where the colour is dominated by different emission mechanisms at different times. That suggests chemistry changing, composition evolving, different processes becoming active as conditions shift. A layered nucleus could explain this. Early on, dust dominates because only the surface is active. Later, as that dust layer erodes, carbon-rich ices underneath start sublimating and produce green emission. Even later, at closest approach, water ice deep in the interior finally reaches sublimation temperature, and the coma becomes dominated by water vapour and its dissociation products, some of which might emit in blue wavelengths under intense solar UV. This is a plausible narrative. It requires the nucleus to be structured in a very particular way, but it is not physically impossible. What we need to resolve this is spectroscopy. Good spectroscopy. High-resolution spectra that can identify individual molecular emission lines, that can measure ratios and temperatures and velocities. The colour observations tell us that something unusual is happening. They do not tell us what. To answer that, we need to decompose the light into its constituent wavelengths, see which molecules are present and how abundant they are, map the chemistry of the coma in detail. December's observations will include extensive spectroscopic campaigns. Hubble, Webb, the Gemini telescopes, Keck, the Very Large Telescope, all have spectrographs. All will be pointed at 3I Atlas during its closest approach. The data they collect will either confirm that the blue colour is from known molecular emission, in which case we update our models and move on, or it will show something unexpected, some spectral signature that does not match any molecule in our databases. And if that happens, if we see emission lines that we cannot identify, then the speculation will intensify, because we will have direct evidence that 3I Atlas is made of something, or doing something, that we have never encountered before. The colour changes are not just pretty pictures, they are data. They encode information about temperature, composition, energy flow, physical state. When we see a comet change from red to green to blue across a few months, we're watching a transformation, a progression through different regimes of physics and chemistry. Understanding that transformation, mapping it to known processes or identifying where it deviates from known processes, is one of the key challenges of studying 3I Atlas. And if the colour remains blue when the comet emerges in November, if weeks after perihelion it is still glowing with that strange azure light, that will be evidence of sustained emission from a source that does not depend on solar distance. That will be evidence that whatever created the blue colour at perihelion is still active, still releasing energy, still making this object unlike anything else in our catalogue of comets. Red to green to blue. 3 colours, 3 states. 3 pieces of a puzzle that we're only beginning to assemble. December 19th, the moment of truth circle. This date on whatever calendar you use to track cosmic events. December 19th, 2025. The day when 3I Atlas makes its closest approach to Earth, passing within 270 million kilometres of our planet. 1.8 astronomical units. Close enough that every major telescope on and above Earth can observe it simultaneously. Close enough that we will finally get the high-resolution data, the detailed spectra, the precision photometry that will either confirm this object is an unusually interesting comet or reveal it to be something else entirely. Loeb has framed this date as the ultimate test of his predictions. If the non-gravitational acceleration detected at perihelion was caused by natural outgassing, by the rocket effect of sublimating ice, then we should see a massive cloud of gas around 3I Atlas in December. Not a subtle enhancement, not a marginally larger coma than expected. A dense, bright, unmistakable envelope of gas that can only have been created by losing 10% of the comet's total mass over the span of a month. The laws of momentum conservation demand this cloud exists if the natural explanation is correct. If the cloud is not there, if 3I Atlas appears in December with a modest coma, with outgassing rates consistent with a typical comet at that distance, then the rocket effect cannot explain the acceleration. Something else must have produced that thrust, and the list of alternatives is short and uncomfortable. Either the mass estimates are wrong by an order of magnitude, meaning the comet is vastly more massive than we think, and therefore does not need as much gas ejection to produce the observed acceleration, or the acceleration was not caused by gas ejection at all. The mass estimates come from brightness measurements and assumptions about albedo. If 3I Atlas is much darker than we assume, if it reflects very little sunlight, and most of its brightness comes from the coma rather than the nucleus, then the nucleus itself could be much larger. A larger nucleus means more mass, which means less mass loss required to produce a given acceleration. This is plausible. We have never resolved the nucleus directly. All our size estimates are indirect, based on how bright the object appears and how we interpret that brightness. We could be wrong. But being wrong about the mass by the factor needed to make the numbers work would require the nucleus to be implausibly large and implausibly dark. It would require 3I Atlas to be the largest interstellar object ever detected by a huge margin, and to have a surface that reflects almost no light at all, which contradicts the spectroscopic evidence showing that the surface is ejecting dust and ice. There is a limit to how much you can adjust parameters before the explanation becomes more unlikely than the phenomenon it is trying to explain. So December 19th becomes a fork in the road. One path leads to a natural comet with an unusual but ultimately explicable set of properties. The other path leads to a genuine anomaly that demands new thinking, new hypotheses, maybe even acknowledgement that we are looking at something that does not fit into our existing categories of astronomical objects. The observation campaign is already being planned. Hubble Space Telescope will use its wide-field camera to image the comet in multiple filters, measuring colours and coma structure with the resolution that only space-based imaging can provide. James Webb will point its near-infrared spectrograph at the target, obtaining spectra across wavelengths that are blocked by Earth's atmosphere, identifying molecules that are invisible to ground-based telescopes. Webb's infrared sensitivity will also allow it to measure the temperature distribution in the coma, seeing whether there are hotspots, regions where heating is stronger than simple solar radiation can explain. On the ground, the Gemini telescopes in Hawaii and Chile will conduct coordinated observations using their adaptive optic systems to achieve near-diffraction limited imaging in the near-infrared. The Very Large Telescope in Chile will deploy its full arsenal, multiple spectrographs operating simultaneously to cover ultraviolet, visible and infrared wavelengths. Keck Observatory will use its cosmic web imager to map the three-dimensional structure of the coma, seeing how gas and dust are distributed in space, rather than just projected onto the plane of the sky. Dozens of smaller telescopes will participate. University observatories, amateur astronomers with equipment sophisticated enough to contribute useful photometry. Automated survey telescopes that can take frequent measurements, tracking how the brightness changes hour by hour. The International Asteroid Warning Network, which added 3I Atlas to its observation campaign as a training exercise, will coordinate tracking across multiple sites to ensure continuous coverage. This is unprecedented. Never before have so many resources been devoted to observing a single comet. 1I Oumuamua was gone before we could mobilize this kind of campaign. 2I Borisov got significant attention, but not at this scale. 3I Atlas has captured the imagination of the astronomical community in a way that previous interstellar visitors did not, partly because of its anomalies, partly because of the Loeb controversy, partly because it will be observable for months, giving us time to plan and coordinate and execute a comprehensive study. The data from December will answer several critical questions. First, what does the nucleus actually look like? Can we resolve it? Can we measure its size directly instead of inferring it from brightness? Hubble has the resolution to potentially see the nucleus as an extended object rather than a point source, especially if the coma is not too bright. If we can measure the nucleus size, we immediately constrain the mass, which tells us how much gas ejection is required to produce the observed acceleration. Second, what is the coma density? How much gas and dust is present around the nucleus? This is measurable through multiple techniques. Direct imaging in scattered light shows dust. Spectroscopy shows gas through emission lines whose strength depends on the number of molecules present. Comparing the two gives you the gas-to-dust ratio, which is a fundamental property that tells you about composition and activity level. If 3I Atlas has a huge coma, if it is surrounded by a dense cloud of material that supports the massive outgassing hypothesis, if the coma is modest, comparable to other comets, that contradicts it. Third, what molecules are present and in what ratios? The spectroscopic observations will identify emission lines, measure their wavelengths and strengths, compare them to laboratory data and theoretical models. We will know whether carbon chains are present in quantities sufficient to explain the green colour. We will know whether the blue emission comes from carbon monoxide ions or from something else. We will know whether there are unexpected molecules, chemical species that should not be there or should not be abundant, that hint at unusual formation conditions or internal chemistry. Fourth, is there any evidence of structure in the coma? Jets, streamers, shells, asymmetries. Active comets often show jets of gas erupting from specific locations on the nucleus, creating patterns in the coma that reveal information about the nucleus rotation and the distribution of active regions. If 3I Atlas shows strong jets, if the emission is highly asymmetric, that could explain the non-gravitational acceleration as a natural consequence of uneven outgassing. If the coma is symmetric, if there are no clear jets, that makes the acceleration harder to explain through standard comet physics. And fifth, has the colour persisted? Will 3I Atlas still be blue in December, or will it have faded back to red or green or white? The colour evolution is one of the most diagnostic pieces of information, because it tells us about the energy source. If the blue colour was temporary, driven by specific conditions at perihelion that no longer apply, then it was probably a natural but unusual phase transition. If the blue colour is sustained, if the comet remains anomalously blue, even at 1.8 AU from the Sun, that suggests an ongoing emission process that needs explanation. The timing of the observations matters. December 19th is the closest approach, but 3I Atlas will be well placed for observation throughout December and into January. The comet will be in the morning sky, rising before dawn, visible for several hours before twilight makes observation impossible. The moon phase cooperates. New moon occurs mid-December, giving a window of dark skies right when we need them. By late December the moon returns, but the comet will be bright enough and high enough that lunar interference will not completely prevent observation. Multiple observations over several weeks allow us to see changes. If the comet is fading rapidly, losing brightness faster than distance alone predicts, that suggests the outburst at perihelion was temporary and the activity level is returning to baseline. If brightness remains constant or declines slowly, that suggests sustained activity, either from continued sublimation or from some internal process that does not depend on solar heating. Time series data is always more informative than single snapshots because it reveals dynamics, evolution, trends that point toward underlying mechanisms. There is also the possibility of surprises. 3I Atlas has already surprised us multiple times. It surprised us with its early outgassing. It surprised us with its nickel emission. It surprised us with its rapid brightening. It surprised us with its blue colour. Every time we think we have figured it out, every time we build a model that explains the existing data, new observations come in that do not quite fit. December might bring more surprises. The coma might have features nobody predicted. The spectrum might show emission lines from molecules nobody expected. The nucleus might look different from what models suggested. Loeb has said that if the massive gas cloud is not present, if his prediction is falsified, it would be evidence that the rocket effect is not responsible for the acceleration and something else must be invoked. But he is also hedged, noting that mass estimates are uncertain, that the required gas cloud might be fainter than expected, that absence of evidence is not always evidence of absence. This is good scientific practice. Predictions should be testable, but not so rigid that a single observation can definitively prove or disprove them. Reality is always more complex than our models. Interpretation is always required. The mainstream scientists who disagree with Loeb are equally invested in December's observations. They expect to see a comet, an active, outgassing, sublimating comet with a composition that is unusual but comprehensible. They expect the spectrum to show the molecules we have already detected, plus maybe a few more. They expect the brightness and colour to be consistent with natural processes, perhaps with some refinement to the models, but nothing revolutionary. They expect 3i Atlas to fit into the box we have built for interstellar comets, even if it sits in a corner of that box where nothing else currently resides. Both sides will get data. Both sides will analyse it. Both sides will publish papers. And both sides will argue about the interpretation, because that is how science works. Consensus emerges slowly when the phenomena are ambiguous. But December will at least narrow the possibilities. It will give us facts where we currently have speculation. It will replace models with measurements. And that movement from uncertainty toward knowledge, however incremental, however incomplete, is what makes the observation campaign worth the effort. 1 month, one closest approach, one chance to see 3i Atlas from the best vantage point we will ever have, and then it will move on, receding into the darkness, leaving us to make sense of what we saw. A message from a dead world physicist. Brian Cox called it exactly that, a message from a dead world. Not in the sense of alien communication or technological artifacts, but in the deeper, more poignant sense that 3i Atlas is a fragment of something that no longer exists. The star system where it formed, the planetary disk where it accreted from ice and dust and organic molecules, the gravitational dynamics that eventually ejected it into interstellar space, all of that happened billions of years ago. The world that created 3i Atlas is gone, changed beyond recognition. Perhaps the star has evolved off the main sequence. Perhaps the planets have migrated or been destroyed. Perhaps nothing remains of the original system except this one icy traveller drifting through the galaxy carrying the chemical signature of a place and time we will never see. That perspective is humbling regardless of whether 3i Atlas is a comet or something more. It is a reminder that we live in a universe where most of what exists is inaccessible to us, where most of history has already happened and left only faint traces, where the objects we study are often the last survivors of processes that ran their course eons ago. 3i Atlas has been travelling for somewhere between 3 billion and 11 billion years. It has witnessed the evolution of the galaxy in ways we cannot imagine. It has passed through regions of space we will never reach. And now, by pure chance, its trajectory happened to intersect ours for a few months. If it is a natural comet, if all the anomalies resolve into unusual but comprehensible physics and chemistry, then 3i Atlas is still teaching us something profound. It is showing us that comets from other star systems can be radically different from comets in our own. That the formation conditions around other stars, the chemical compositions of other planetary disks, the processes that shape and age interstellar ice over billions of years, all create diversity we have barely begun to explore. Every interstellar object is a data point about the galaxy as a whole. Every observation of these rare visitors expands our understanding of what is possible, what is common, what is strange in the cosmos beyond our immediate neighbourhood. The age estimates are particularly striking. 7.5 billion years old. That is older than our solar system by more than 50%. The Sun did not exist when 3i Atlas formed. Earth did not exist. Life did not exist. The galaxy looked different. With more young stars, more active star formation, a different distribution of metals and heavy elements. Whatever star system created 3i Atlas was part of an earlier generation, formed from material that had been through fewer cycles of stellar birth and death. The chemistry should reflect that. The isotope ratios should be different. The trace element abundances should tell a story about nucleosynthesis processes that occurred billions of years before our own solar system began. This is why spectroscopy matters so much. We are not just measuring what molecules are present right now as the comet sublimates. We are measuring what elements were available in that ancient star system, what conditions existed in its outer reaches where volatiles could condense, what kind of radiation and cosmic ray environment the nucleus experienced during its journey through interstellar space. Every emission line, every isotope ratio, every molecular abundance is a clue about the history encoded in this object. If the carbon dioxide dominance is real, if 3i Atlas truly is 87% carbon dioxide by mass, that tells us something about temperature and pressure in the disk where it formed. Carbon dioxide preferentially condenses in very cold environments, colder than the regions where most solar system comets formed. This suggests 3I Atlas originated far from its parent star, perhaps in the equivalent of our Oort cloud or beyond. It was born in the deep cold and has remained cold ever since, never approaching close enough to a star to lose its volatile ices until now. The nickel without iron signature, if it persists in December observations, points to chemistry we do not fully understand. Natural astrophysical processes always produce nickel and iron together because they are synthesized together in supernovae. They are both iron group elements with similar properties. They condense together in stellar outflows. They should be inseparable. Yet 3I Atlas is emitting nickel prominently while iron remains undetected. This could mean the formation environment had unusual conditions, chemistry that preferentially incorporated nickel over iron. Or it could mean the nucleus has been processed somehow, altered by some mechanism that segregated the two elements. Or it could mean we're seeing an industrial signature, the result of refining processes that do not occur naturally. That last possibility is what keeps Loeb in the conversation. It is what prevents mainstream astronomers from completely dismissing his arguments. Because even if the probability is low, even if every instinct says this must be natural, the nickel signature is genuinely hard to explain. And when you couple it with the other 8 anomalies, when you look at the full suite of properties rather than any single one in isolation, the cumulative improbability starts to weigh on you. It starts to feel like something needs to give, like our models need to stretch further than they comfortably can, like we are being forced to accept too many coincidences. The trajectory through the solar system is one more piece of this puzzle. 3I Atlas will pass near Venus in early November 2025. It already passed near Mars in October. It will pass near Jupiter in March 2026. Its path takes it through the plane where all the interesting objects are, where all the potential targets for observation or interaction reside. If you were designing a mission to survey a star system, if you wanted to visit multiple planets in one pass, this is the trajectory you would choose. You would align with the ecliptic. You would time your perihelion to coincide with favourable planetary positions. You would maximise the science return from your flyby. Of course, natural objects can also follow such trajectories. Comets from the Oort cloud occasionally come in on ecliptic-aligned orbits purely by chance. The probability is low but not zero, and we've observed enough comets over the centuries that eventually the unlikely ones appear. 3I Atlas might just be one of those unlikely cases, a natural object that happens to have a trajectory that looks optimized because the geometry happened to work out that way. But it is worth asking what we would see if an interstellar probe did visit our solar system. What signatures would betray its artificial nature? What observations would distinguish it from a natural comet? Loeb has argued that most of the anomalies of 3I Atlas are exactly what you would expect from a technological object. The orbital alignment, the unusual composition, the acceleration without visible outgassing, the size and speed, the fine-tuned trajectory. If all of those properties appeared in a human-made spacecraft, we would instantly recognize it as artificial. We give it a pass as natural only because we assume the alternative is too improbable to consider seriously. That assumption might be wrong. We have no idea how common technological civilizations are in the galaxy. We have no idea how many might have built interstellar probes. We have no idea what fraction of those probes might pass through our solar system in any given century. The numbers could be zero, they could be small, they could, in a sufficiently old and densely populated galaxy, be large enough that encountering one in a human lifetime is not absurd. We do not know. And in the absence of knowledge, we default to skepticism, to the assumption that the universe is mostly natural and technology is rare. But that assumption is just an assumption. It is not based on evidence. It is based on priors, on what feels reasonable given our limited experience. 3I Atlas is testing those priors. It is asking whether we are willing to update our beliefs when confronted with anomalies, whether we are open to possibilities that seem unlikely but cannot be definitively ruled out, whether we can hold multiple hypotheses in mind simultaneously without prematurely collapsing to the one that feels most comfortable. The observations in December will help. They will provide data that constrains the possibilities, that makes some explanations more plausible and others less, but they will not provide certainty. They will not definitively prove 3I Atlas is natural or artificial. They will move the needle, shift the probabilities, give us more information to work with, and that is all science can really do when dealing with unique, ambiguous phenomena that do not fit neatly into existing frameworks. In March 2026, 3I Atlas will pass near Jupiter. The Juno spacecraft in orbit around the gas giant might be able to observe the comet from yet another vantage point. Europa Clipper, if it has arrived in the Jupiter system by then, could add its instruments to the campaign. These observations will be the last good look we get before 3I Atlas leaves the solar system entirely, heading back out into the interstellar medium from which it came, and then it will be gone. Another object in the catalogue, another paper in the journals, another debate that never quite resolved itself because the evidence was insufficient and the phenomenon too fleeting, unless something dramatic happens. Unless the December observations reveal something so anomalous, so clearly outside the bounds of natural behaviour, that even the skeptics have to acknowledge we are looking at something extraordinary. That is the hope and the fear. The hope that we might witness something genuinely unprecedented, something that expands our understanding of what exists in the universe. The fear that we might discover we are not alone, that other intelligences are out there, and that we have been too blind or too cautious to recognise the signs when they appeared in our telescopes. Either way, 3I Atlas has already succeeded in making us question our assumptions. It has forced conversations that would not otherwise have happened. It has pushed scientists to articulate why they believe what they believe, to defend their positions with evidence rather than authority, to engage with uncomfortable ideas rather than dismissing them out of hand. And it has reminded us that the universe is full of mysteries, that we have explored only a tiny fraction of what exists, that every new object, every strange observation, every anomaly that defies easy explanation is an opportunity to learn something we did not know before. Whether 3I Atlas is a comet from a dead world or something more, it is teaching us, and we should be grateful for the lesson, however it ultimately resolves. The ancient ice remembers. It carries information about a time and place we cannot visit, about chemistry and physics, and perhaps about the ambitions of beings we have never met. All we can do is look, measure, analyse, and try to understand the message encoded in those frozen molecules, racing through the darkness at 61 kilometers per second. A message from a dead world, or a messenger from a living one. December will bring us closer to knowing which.